Good morning. Today we're going to talk about logarithmic functions. Remember last time I talked about exponential functions and I repeatedly reminded you that learn the nature of the exponential function and their graphs because it is going to help us tremendously when we will talk about logarithmic function. So we're going to start by reminding ourselves the basic properties of exponential functions. So exponential functions. If the function looks like y equal to b to the power x with b not equal to 0, b not equal to 1, and b strictly greater than 0, we call it exponential. The letter b is a constant and we call it the base. So b is a constant and it is called the base. Real quick, there are two types of graphs that we can expect for exponential functions. One is for the base being strictly greater than 1, and that rises to the right hand side and falls down to the height 0 on the left hand side. Has the y-intercept at the point 0, 1. The other type of graph is for the base being between 0 and 1, and the basic graphs are mirror reflection of b greater than 1 situation along the y-axis. So it rises on the left hand side and it falls down to the height 0 on the right hand side, even though the y-intercept still remains 0, 1. And we talked about a bunch of properties, and I want to remind you some of these properties as well. We talked about the domain, and we said the domain of either type of exponentials are negative infinity to infinity. We talked about the range, and we said that the ranges are always 0 to infinity. There is no x-intercept, and the y-intercept is always the point 0, 1. We talked about asymptotes. We said that there is no vertical asymptote for exponential functions, whereas there are horizontal asymptotes, and the horizontal asymptotes for the basic exponential functions are given by the x-axis, which is the height y equal to 0. We also talked about the long-run behavior for exponential functions, and we said that as x goes to infinity, for b greater than 1, y goes to infinity on the right-hand side, whereas as x goes to negative infinity, for b greater than 1, the left-hand side, y goes to 0. Whereas as x goes to infinity, for the situation 0 less than b less than 1, on the right-hand side, y goes to 0. And as x goes to negative infinity, on the left-hand side for the situation 0 less than b less than 1, y goes to infinity. What is a logarithmic function? A logarithmic function is the inverse function for an exponential function. What does it mean? If x is your input and you do the inverse, the exponential function, then your output is b to the power x. So x being the input, the output is b to the power x. So what is logarithmic function? The logarithmic function will take this output b to the power x and will give you the input x. So in other words, b to the power input is equal to output is the exponential form log, log for logarithmic function, of the output, and we say with respect to the same base b, is equal to the input. That's the basic definition of logarithmic function. So to say, we're going to now formally define a logarithmic function, and we will say that if y is equal to b to the power x, then log of the output, as you can imagine that's y, with respect to the same base b, should be the input x. And vice versa. If y is equal to log of x to the base b, then b to the power in the exponential form, the output y is equal to the input of the logarithmic function, which is x. So y equal to b to the power x implies in the logarithmic form log of y to the base b is equal to x, and if you have log of y to the base b equal to x, then you get to come back to the exponential form y equal to b to the power x. Now this mirror reflection, this mirror imaging of exponential and logarithmic function will be understood a little better when we will actually start talking about the graph of the logarithmic function. So as I have said, we are going to read log of x to the base b as log of x to the base b. And this logarithmic function is the inverse of the exponential function. Remember from our inverse function class, I said the graph of the inverse function and the original function are mirror images of each other along the straight line y equal to x. So let's try to understand, if this is the graph of b to the power x, what will be the graph of the inverse function log x to the power base b? Well, think about the line y equal to x, because I'm going to reflect the function. So this is y equal to x. Remember the point of y-intercept. This is 0, 1. In the inverse, you switch the x and y, so it has become 1, 0. And you take the mirror reflection of your exponential function and you get something like this. And that will be the graph of log of x to the base b. Similarly, in the other situation, we have the graph of b to the power x. Whenever b is between 0 and 1, I'm going to take the mirror reflection of this graph along the line y equal to x. So we'll draw y equal to x. Again, the point which was the x-intercept, the y-intercept, 0, 1, will become the x-intercept, 1, 0. And I will take the mirror reflection of my graph, and what I will end up is something along this line. And that will be the graph of y equal to log of x to the base b. The reason I wanted to do it because I want to compare the properties between exponential and logarithmic function, which is a fun thing always. Remember, logarithmic and exponential functions are inverses to each other. So whatever was x, now it is going to be y for log. So this is b to the power x. Now we're going to study the property for y equal to log x to the base b, the inverse function. How about the domain? So domain was x, so that should be y for the inverse function. This is x property, domain is x property for the function, should be the inverse property is y property. So the range of the logarithmic function is negative infinity to infinity. And you can see that from the graph. As you can see in both green graphs, your graphs are falling down to negative infinity and going up to positive infinity. How about the domain of the logarithmic function? Well, you were looking for x in the inverse. That should be y in the original function. So the range of the original function is 0 to infinity. Must say the domain for the logarithmic function is 0 to infinity. It's basic switch between the variable information from x to y. There was no x-intercept for exponential, so there is no y-intercept for logarithmic function. There is y-intercept for exponential function, so there will be x-intercept for logarithmic function, and that will be the point 0, 1. Well, you have to switch the x and y coordinates, so it should be equal to 1, 0. Asymptotes. Remember, there is no vertical asymptote for exponential functions, so there is no horizontal asymptote for logarithmic function. No horizontal asymptote. Whereas there is horizontal asymptote for exponential. So this time it will be vertical asymptote for logarithmic function. And the vertical asymptote will be given by x equal to 0. It was y equal to 0, so now it will be x equal to 0. And I can verify that from the graph as well. Look at your functions, the green functions, they are coming closer to the y-axis. One on the downward direction and the other one on the upward direction, but they're coming closer to the y-axis, which is x equal to 0. As x goes to infinity, for positive b, y goes to infinity. And for logarithmic function, the long run behavior, this is the only place where we have to be a little careful. For logarithmic function, the long run behavior is going to be written this way. As x goes to infinity, if I look at the logarithmic function for b greater than 1, then y goes to infinity as well. For b greater than 1, as x goes to negative infinity, y goes to negative infinity for b greater than 1. Whereas if x goes to infinity, y goes to negative infinity for the b being between 0 and 1, and as x goes to negative infinity, y goes to positive infinity for b being between 0 and 1 in the second graph for a logarithmic function. So all the properties except the long run behavior can be understood just recalling the very fact that function and inverse functions are obtained by interchanging variables x and y. So I will again put a note here saying that long run behavior cannot be realized by the interchange of the variables. It doesn't work that well. Okay, so we're going to try to understand logarithmic function a little better. So we'll go to our example number 1. This one says that if you are already a logarithmic equation, change to exponential equation. If you are already exponential equation, change to logarithmic equation. And I'm going to constantly use those terms, input, output. So the first example is logarithmic. The output is 9, the input is m, base is 6. So base remains base. Input becomes output. The input was m, so it will be equal to the output. The output was 9, so it will be equal to the input. So 6 to the power 9 equal to m is the corresponding exponential equation. So it was logarithmic, I have shown you how to change it to exponential equation. Similarly, for your next example, you have exponential, you want to write a logarithmic expression. What else you need? What is the base? Well, the base is e, so I have to go ahead and write the base. The input is x, so that should be the output. The output is 5, so that should be the input. So log of 5 with respect to base e is equal to x. Similarly, you have exponential, change it to logarithmic. As soon as you say change it to logarithmic, I will go ahead and write logarithmic. Input is negative 5 over 2, so that should be the output. Output in the exponential is 1 over 32, so that should be the input. And the base is 4, so it's log of 1 over 32 to the base 4, answers in negative 5 over 2. The second set of example, I have 3 exponential function and I'm going to write the equivalent logarithmic function. So log, think of the base, that is a. Think of the output, that is 473, so that should be the input for the log. Think of the input, that is 5, should be the output for the log. Similarly, base is 10, so I will say log base 10. Input is 3, that should be the output for the log. Output for the exponential is 1000 should be the input for the log. Log base is 216. Output for the exponential is 6, input for the log. Input for the exponential is 1/3, output for the log. Answers for the equivalent form of exponential and logarithmic equation. Since we have seen bunch of different properties for exponential functions, there are some that we can use to define properties for logarithmic function. For example, remember the fact b to the power 1 is always equal to b. That's exponential. Let's write it in terms of logarithmic. So log, the base is b, the output of the exponential is b, so should be the input of the log. The input of the exponential is 1, so should be the output of the log. What does that tell me? That log of b to the base b is always 1, doesn't matter how much is the base. As long as the base and the input of the log are the same number, your answer is always going to be equal to 1. Similarly, think about b to the power 0. For exponential function, this is always 1. Change it to logarithmic function. So log, base is b, output of logarithmic function is 1. Output of the exponential function is 1. So input of the logarithmic function is 1. Input of the exponential function is 0. So output of the logarithmic function is 0. So log of 1 to the base b is always 0. Doesn't matter how much is the base. As long as I'm taking log of 1, the answer is always 0. Since logarithmic function and exponential functions are inverses to each other, if I do logarithmic function followed by exponential function, or I do exponential function followed by logarithmic function, I always get the answer x because they are inverses. And those are called inverse properties. So see this one, the inside function is exponential, the outside function is logarithmic function. Both of them have the same base. So as if I have cancelled all the log and the exponential terms and I just got the input. Similarly, inside is log, outside is base, exponential. So everything cancels, you get x. And that happens because the exponential and logarithmic functions are inverses to each other. All these four properties that I have talked about are extremely important for our further understandings. Evaluate each expression without using a calculator. So let's try to do that. The first one is log 7 cube root of 7 to the base 7. So what I do, I write it as log of 7 to the power 1/3 to the base 7. Now think of this. This is the inverse property. You have the exponential as inside, log as outside. Both of them have the same base. So cancel everything and your answer is just going to be the input 1/3. So log of cube root of 7 to the base 7 is 1/3. I will do the same thing on the next problem. I will write it as log of 16 to the power -1 to the base 2. Can't do anything with it yet. So now you're going to write it as log of 2 to the power 4. Remember 2 to the power 4 is 16 to the base 2. And 16 to the power -1, so I will write it this way. But then I know power of power is simply multiplying the powers. So I get log of 2 to the power -4 to the base 2. Now you have inside exponential, outside log, both of them base 2. So they cancel each other and you get -4. The third one is a decimal number. So what I do to simplify, I write log of, instead of 0.125, I write 125. I count the number of decimal places. There are 3. So it's 1000. I need 3 zeros to the base 8. Then I will simplify the fraction 125 over 1000. And it turns out I can divide both top and bottom by 125 and I will get 1 over 8. So I have log 1 over 8 to the base 8. See, that is log of 8 to the power -1 to the base 8. Exponential inside, logarithmic outside, both of them same base 8. So they cancel each other and I get the input equal to -1. So I have shown you how to solve each of these logarithmic expression without even using a calculator. How about example for the first one? Well, it is asking you to find log of 1 to the base 4. Remember, log of 1 to the base anything is 0. And I answered it. The next one, write 3125 as a power of 5. So you will get log of 5 to the power 5. It will take you a couple of minutes. 5 to the power 5 is 3125. I know that, so I can do it in seconds. But then see, exponential inside, log outside, both with respect to base 5. So they cancel, and I get the input 5. Answers my question. Then I have talked about the graph of the logarithmic function and all the basic properties of logarithmic function. So we'll skip them and go start talking about transformation and understanding log. See, it is like the exponential function questions. We're going to understand the transformation, talk about domain, asymptote, and range of the functions. So the first example is, if you know the graph of log of x to the base 3, can you do the graph of log of x plus 3 to the base 3? Remember, log x to the base 3 looks like this. That's the basic graph. This is 3 is the base, and that's greater than 1. So this is the basic graph for the function log of x to the base 3. Now this means shifting 3 units to the left. That means you are subtracting 3 from your x coordinates. So see, original versus changed, and I'm going to do the exact same work that we have done in exponential function. The original domain of logarithmic function is 0 to infinity. The range of the logarithmic function is negative infinity to infinity, and the asymptote is a vertical one, but it is given by x equal to 0. So let's see what changes I am doing. Remember, your change is subtracting 3 from the x-axis. So you get 0 minus 3, infinity minus 3, because these are x on the domain, and the answer is going to be negative 3 to infinity, as I can subtract anything from infinity, will not essentially change anything. Range, well, did not change anything on the y-axis, so it stays negative infinity to infinity. But I did change the x-axis, so asymptote will be now 0 minus 3, because you shifted it 3 units to the left, so subtract 3, and you get x equal to negative 3 as the vertical asymptote. It is a shift of the original graph 3 units to the left, so I will say B is your right choice. And as you can imagine, if I drop this vertical asymptote, it is the line x equal to negative 3. And every other information for domain, it's negative 3 to infinity makes sense. The range becoming negative infinity to infinity makes sense. Let's do a similar one. This time, I'm going to do 1 plus log x to the base 3. So this one talks about shift up by 1 unit. So you're going to add 1 to your y coordinate. So again, I do the listing for original versus the changed ones. The original domain of logarithmic function being 0 to infinity. And since in this transformation I did not change x, the domain remains 0 to infinity. Remember, your change is only in y and you added 1. Range is in y, so there should be some changes. So I will add 1, but again, adding 1 to negative infinity or infinity doesn't change them. They're so big, it still remains negative infinity to infinity. Asymptote is vertical this time, so it is given by x equal to 0. I changed y, so I did not change x, so it remains x equal to 0. Now think about the graph. It is shifted up by 1 unit, so I'm going to go pick the 4th graph, which is shifted up by 1 unit, and see the vertical asymptote remained at the y-axis, so x equal to 0. So the domain did not change, it's still 0 to infinity. The range is negative infinity to infinity. The other major type of problems that I can ask you from basic logarithmic function is going to be finding the domain of a morphed logarithmic function. So you know that logarithmic function, the domain requires the input to be positive. So look at the input of the logarithmic function, whatever function it is, and that should be strictly greater than 0. For example, in this function, the first one, the input is x squared plus 6x minus 7, and I want it to be greater than 0. and I solve the polynomial inequality. So factor it. Your factors are x plus 7 and x minus 1. So the critical points are -7 and +1. So I do the number line. I get -7 and 1, and then I take testing points. So let's call -8. 0 is good. That's between -7 and 1. And 2 as my testing points. What happens at -8? Well, -8 plus 7, I'm using the factors. And -8 minus 1, both of them are negative quantities. So when I multiply them, I get positive. And remember, I wanted positive as my sign. So 0. For 0, you get 0 plus 7 times 0 minus 1. First one is positive, second one is negative, total sign is negative. I don't want that. The last testing point is 2, and I get 2 plus 7 times 2 minus 1. Both of them are positive, hence I get positive, and I want it. So now you're going to list the intervals where the function is positive. And that will be the domain of this logarithmic function. So the domain for this logarithmic function is going to be -infinity to the critical number -7, and I have to put open because both of these points are not going to be included as my inequality is strict. And then I will say union 1 to infinity. The second example is a mixed example. This is one example where I have square root function and I have logarithmic function. And because you can think of this thing as the algebra, the subtraction between two functions, we will talk about the overlap of the domain. So let's first talk about the the logarithmic function. The input is x plus 8 for the logarithmic function. And x plus 8 must be strictly greater than 0, so x must be strictly greater than -8. I'm done with that much. For x minus 7 being the term under the square root, that cannot be non-negative. That should be non-negative, I'm so sorry. Cannot be negative. So it should be greater than or equal to 0. So x must be greater than or equal to 7. Number line. The 2 points are 7 and -8. -8 being smaller, it's on the left-hand side. This one must be open, this one must be closed by the equality and non-equality. First one says that your x must be greater than -8. That's for log. For the square root function, I must be greater than or equal to +7. What is the overlap of these two colors? It's from 7 to all the way infinity. So the domain, being the domain of the algebraic subtraction between these two functions, will be the overlap closed 7 to +infinity. And would answer your question. The next list is talking about two spatial logarithmic functions. So these basic logarithmic properties, that log of 1 is always 0, log of b with respect to base b is always 1, log of b to the power x with respect to base b by the inverse rule is x, b to the power log x to the base b is always x. Also applies if the base of the logarithmic function is 10. And we call it a common log. And we do not write the base. So if you do see logarithmic term without the base, by default you know that the base is 10. And all these properties are good. Remember what I'm saying. Log of 1 with respect to base 10 is 0. Log of 10 with respect to base 10, because the base and the input are the same, is 1. Log of 10 to the power x to the base 10, you cancel everything, get the input. 10 to the power log of x to the base 10, you cancel everything, get the input equal to x. Similar properties are true for logarithmic function with base e. Remember the number between 2 and 3? Those are called natural logs, and hence I use ln. So if I write ln, you know that I'm writing log to the base e. So log of 1 to the base e, which is natural log of 1, must be 0. Log of e to the base e, because the base and the input are the same, must be 1. Log of e to the power x to the base e, everything cancel, you get the input gives you natural log of e to the power x equal to x. And e to the power log of x to the base e, everything cancels, you get the input, so e to the power natural log of x is equal to x. I just used different notation for the common log and natural log, and we're going to keep using this notation for common and natural log. So let's do a couple more problems. Evaluate the expression without using a calculator. So I'm trying to find out log of 7 to the base 7 to the base 3. So let's do the inside first. See, the base and the argument or the input are the same, so that value must be 1. So we'll get log of 1 to the base 3. But if I'm taking the log of 1, doesn't matter how much is the base, answer is always 0, and you're done. The next problem is finding the domain of the logarithmic function. So again, think about the input. The input in this logarithmic function is x squared minus 4, should be greater than 0. What does that tell me? Well, x squared must be greater than 4. Take the square roots on both sides. So you get absolute value of x greater than 2. What does that mean? It's twofold answers. X is greater than 2 or x is less than negative 2. Let's see it on the number line. You have negative 2, you have positive 2. Either you are greater than 2 because of non-equality, strict inequality, I would put open dot, or I am less than negative 2. So I'm on this side. So that tells me the domain of this function. The domain is negative infinity to negative 2 union 2 to infinity. You could have solved this as a polynomial inequality as well. For example, I could have said x squared minus 4 greater than 0 means x plus 2 times x minus 2 is greater than 0, as these are the factors. And then I would be able to say that then the critical numbers are negative 2 and 2. So number line I got negative 2 and 2. I will take testing points. I will take negative 3, maybe 0 and 3. And see, at negative 3, if I use the factored form, I get negative 3 plus 2 times negative 3 minus 2. Both of them being negative, I get negative times negative, which is positive, so that's good. For 0, I get 0 plus 2 times 0 minus 2. The first one is positive, the second one is negative, so total sign is negative, not good. And then for 3, I get 3 plus 2 positive, 3 minus 2 positive. So both of them are positive, meaning total sign is positive. So I take that interval. So anyhow, in either way, you can find the domain in this way. Then I'm finding the domain for natural log of x squared plus x minus 2. Well, input. The input for this logarithmic function is x squared plus x minus 2 must be greater than 0. Factor. X plus 2 times x minus 1 must be greater than 0. Critical numbers. The critical numbers are negative 2 and positive 1. I will not take them because of strict inequality. And then I will talk about testing points. So let's say negative 3, 0 is good here, and I can take 2. For negative 3 in the factored form, I get negative 3 plus 2 times negative 3 minus 1. Both of them are negative signs. So multiplying 2 negative will give me a positive, and I will take it. That's good. I wanted positive. For 0, I get 0 plus 2 times 0 minus 1, which is positive times negative. That's negative. Bad. Not going to take it. 2, I will get 2 plus 2 times 2 minus 1. And see, both of them are positive. Total sign is positive. You wanted positive for your domain. So these are the two intervals you will take. And I will say domain of this logarithmic function is negative infinity to negative 2 open union 1 to positive infinity. One more domain question, but this one is also asking for range. Because I'm talking about logarithmic function, I don't even have to work anything. I will just go ahead and say the range is negative infinity to infinity. No problem there. Domain is what I'm interested in. So input for this logarithmic function is 13 minus 2x should be strictly greater than 0. So 13 should be strictly greater than 2x. Divide both sides by 2. So you get 13 over 2 greater than x. So in other words, you get to say x is less than 13 over 2. Number 9, get your 13 over 2. Your x is less than 13 over 2, so you are on the left hand side. You don't take 13 over 2 because of the strictness of the inequality. So the domain is given by negative infinity, comma, 13 over 2 answers your question. And that is the basic definition of logarithmic function. I encourage you to do all your homeworks in Top Hat before we come for the class for properties of logarithmic function. We have defined both exponential and logarithmic function. These are not simple concepts. It will require you to do a bunch of exercises before you can eventually get a good grasp of the concept. So I encourage you to do your homeworks. Let me know if you have any further questions for me. Email me. I will get back to you as soon as I can. And I look forward to talk about properties of logarithmic function next time with you. Goodbye.